All right, so what we want to do is we want to use Newton's method on this function with this initial value, and we want the first 10 iterations. I won't do all 10 because it's busy work, but I'll do the first couple and you'll clearly see what the pattern is. So Newton's method depends on the derivative. So given this function f, we can see here quickly that the derivative is that. So this is essentially the given information. Now, we know this is what we want. We know what x naught is. The initial guess is 6. That takes care of that. Now we got to find x1. In order to do that, why don't you make a list over here? Let's pretend that n equals 0. Let me focus my camera. Let's pretend that n equals 0 because watch. When I replace all of these n's with 0, especially there, 0 plus 1 is 1. So when n is 0, I am finding x1, and that's good because I need to know what that is. So let's see, all these n's become zeros. So this would be x0 minus f of x0 over f prime of x0. And let's see, we know what x naught is, or x0, whatever you want to call it. It's just 6 minus f of 6 over f prime of 6, and that's 6 minus, what's f of 6? Well, f is the original function. Plug 6 in there, 36 minus 26 is 10. And f prime is the derivative, so plug 6 into the derivative, that's 12. And why don't we go here? And I get 31 over 6, which is a nice exact value, but I think they wanted you to round to 6 decimal places. So, oh boy, let's see. So this is, it was 5.1, and then the 6's go on forever, endeavor. But they wanted you to round to 6 decimal spots. So let's see. Who am I going to round? 1, 2, 3, 4, 5, 6. I am going to round this digit. So I look after it and I see a digit that's 5 or bigger. And so this one becomes a 7. So in my answer key, I have 5.166, and then 2 more 6's, and then a 7. 1, 2, 3, 4. So this is now the value of x1. What do we do next? We now pretend that n is 1. So let me just do this one, and then I'll let you do the rest because it really is busy work, and it's just going to take like 30 minutes to do. So let's pretend that n is 1. So I plug 1 in for all these n values, and that'll of course be, so this is what it'll say. When n is 1, you plug 1 in there, 1 plus 1 is 2, all these stay 1s. So now, what exactly is x1? It's this number there, so it's, so this is what we get, right? We get x1 minus f of x1 over f prime of x1. Now we go to our Casio calculators. And if I round this to the 6th digit, I get 5.09946. Hold up. I'm going to round 1, 2, 3, 4. I'm going to round the 2. After the 2, there is a 3, so the 2 stays 2. And that is my official answer for x sub 2. So 5.099462. So look, let me just say this, then I'll let you go. You need the first 10 iterations. That means that you should continue down all the way to n equals 9. You stop at n equals 9 because when n is 9, you're going to get x sub 10 down here. And also, let me tell you this before you go. What are we trying to do? This is what is going on. F of x, x squared minus 26 is a parabola. And it looks something like this. Watch this. Not the best picture, but it communicates the idea. What you're trying to do is you're trying to find that number there. Really, you're going to find that as well, but this is what you want. How can you find this? Well, you'd have to let the function equal 0. So watch what I do. If I plug 0 into the function, I get x squared minus 26. Solve that, you get x equals the square root of 26, which they didn't have calculators hundreds of years ago. So there is no way that they could find this number that I just found. So they had to do this primitive method. So what's going to happen is, as you go down this list here, your 10th iteration is going to be awfully close to this number, the square root of 26. As a matter of fact, each subsequent iteration should be getting closer. Notice that this one is already awfully close, and that's only the second iteration. By the time you're down here, this number is going to be very close to this. So you can expect that to happen as you do this work, as you do the rest of this problem on your own.